Yes, thank you so much for the kind introduction, and thank you for inviting me to be here. It's really a great pleasure. As you heard from the introduction, a lot of the things I work on, you should know that a lot of these kinds of techniques are inspired by the work that's come out of this department, both for the giant Bayesian cohort and many nice new connections, as well as other things that I won't talk about today, but on things like covariance estimation and doing a lot of computation in different domains, be it wavelets or Fourier bases. So um, really just, for the students here, there's a lot of great ideas that came out of here, so you should work hard and be like your mentors. And today I will talk about just one slice of this work, but my goal is to more or less just paint the picture on one perspective in doing inference for these kind of epidemic models, right? So we've heard a lot about epidemic models, not only in statistics, but in many literatures ever since the pandemic, especially. And a lot of there's a lot of words being thrown around, like there's this SIR model, there's doing inference with likelihoods, but a lot of it is not as connected to sort of classical inferential machinery and sort of rigorous principled inferential tools. So this is meant to be a more or less motivation for where these challenges arise statistically and how we might revisit some of these classical tools to do principled inference, starting from simpler models. So I mean it to be mostly, if you have any questions, clarifying questions in between, please let me know. I don't want it to be too scary, even though we have a little bit of technicality on the slides, just to lend some concreteness. Although it's Friday the 13th, so maybe it'll be a little scary. But let's go ahead and get started. Again, please feel free to interrupt with any questions. You don't have to wait until the end if you have any clarifying questions. So let's get started. First, as a point of departure, in epidemic models, one of the long-standing mathematical traditions in modeling these processes is using these compartmental models, also called stepping stone models. So one of the most canonical in epidemics is called the SIR, or susceptible, infectious, and removed model. And so this is, this is used even though it's such a simple one. You can draw it in a simple diagram, and it describes how the disease moves through a population in terms of compartments that describe disease status. Right, so if you're susceptible, there's going to be some rate of getting infected that will move you into the compartment of infectious people who then somehow interact with the other susceptibles and then also recover at some rate, right? So this is kind of one of the simplest models, but it is a mechanistic model in that we're using the knowledge or expectation of how these things occur, the dynamics of infection, in particular, interactions between two compartments, to describe the system. And in this sort of original work, it was all deterministic. So there's no statistical model or stochastic part of the process. This is almost 100 years old. So in particular, in these ODE models, we can write these interactions and how this moves in terms of differential equations. Right? So we won't talk about that much, but indeed, if you see a lot of papers outside of statistics talking about SIR or these compartmental models, I'd say the vast majority are working with the deterministic version. So even if they say things like likelihoods, sometimes there's a likelihood based on the noise from this deterministic mean. And I want to put that up there because in contrast, what I want to focus on today is the stochastic version, right? So we're all statisticians, we're a little biased towards statistical models. And it's very analogous in the sense that I'm replacing the instantaneous change rates described by derivatives instead by instantaneous jump probabilities. So you can see that the beta SI, these are kind of the same forms, but instead of DDT of a population, I'm writing them as the probabilities of discrete events. You can have an infection occurring, and in a small enough time interval, the probability looks something like beta times S times D times that interval's length. Similar for recovery, and then when we talk about these kinds of jump processes, we often also write down the probability of no event occurring. But basically, it's a Markov jump process or a continuous time Markov chain. One nice thing about this is A, it's stochastic, but B, we are talking about this on a discrete space, right? The infections are going up and down by one, et cetera. And that can really help because in small populations, the large scale deterministic limits may not hold. So far, this is the model setup, and I'll say a little bit more about continuous time Markov chains as a brief primer soon. Another couple assumptions that are implicit in these simple models, it's oftentimes we're assuming there's a closed population, even though there are ways to relax that. I'll focus on that. And what that lets us do is to mostly talk about it as a bivariate process. Like if I talk about the S and I population, then the other one can be recovered by subtracting from the total. And then another thing here, which is implicit in the way we write this down, I'll talk about here, is we're assuming sort of a random mixing in the population. So if my infection rate is just the product of the total number of susceptible and infected people, it's more or less assuming that the dynamics of interaction is just everyone's kind of bumping into each other in a homogeneous, which is how infections might occur. Okay, so far so good, I hope. So the nice thing about the stochastic models, right, of course, as you know in statistics, if you have a stochastic model, even given a fixed set of parameters, maybe beta and gamma for the infection and recovery rates, you can have different realizations of the process. And they look a little bumpier because these are counting processes now. The other thing is that I do want to, it's a little bit subtle, but statisticians will appreciate that I would say that these mechanistic models that are also stochastic are more interpretable. So one thing that you might have seen even in news articles is epidemiologists and public health people like to talk about quantities such as the basic reproductive number, which is described as something like the average number of secondary infections from an individual. So basically, if you're infected, how many cases are you expected to lead to, right? And so when I say things like average, first of all, it has a particular interpretation in random variables, right? Like if I have an exponential distribution, there is a mean of that distribution. And also in this particular model, this quantity is well defined in terms of the model parameters. But in contrast, if you ever do any of the mathematical modeling from the deterministic side, you have to say, this is sort of a next generation matrix that's depending on the second eigenvalue of something, something. And we can get our hands around that, but a lot of people who are not in mathematical sciences, it's much harder to interpret. And also the notion of average is more opaque. It's not just the average in terms of a random. So this is some motivation. So what I claim is that even that simple model, right? I haven't added bells and whistles to this, and we've seen all sorts of variations of these simple models. It's already difficult to do what I would call classical inference, right? So maybe exact inference in some way. And so I'll talk more about what I mean by that fully. But first, I want to survey what people often do if you buy that it's difficult to do inference to fit these simple models even to data. So it's quite common to do some kind of approximation. So when you see people doing likelihoods for SIR models, they might be a discrete time SIR model, where you kind of like look at discrete generations and it's more or less a sequence of binomials. There might be a univariate branching process that's appropriate for the early stage of an outbreak and seeing when it takes off. It might be continuous state approximations, kind of like mirroring the ODE things, but maybe with a diffusion or something like that. And as well as many others. You can make some parts of it constant, et cetera, et cetera. When we're working with the stochastic models, I would say the predominant approach for inference is based on simulation methods. And so I actually don't really have an issue with these. I think they're very flexible and powerful. And what I mean by simulation-based methods, also called plug-and-play methods, is that they're largely based on simulating realizations of your process, basically synthetic data from various parameter values, and then trying to do some algorithm on filtering those parameter values into getting the most likely. So things like particle filtering or sequential Monte Carlo or various versions of approximate Bayesian computation are very, very widely used for these kinds of models. So they're developed by strong groups from the UK. We have people like Omiros and Gareth Roberts has done some of this, as well as strong groups all over the departments here. But one notable one that's been adopted by practitioners, there's this package called POMP, and it came out of Michigan. So these are very powerful. But I would say that oftentimes we don't want to rely on just simulating a lot of data. Not only can that be computationally intensive, but these are kind of well documented for having certain degeneracy issues or like kind of the particles all kind of, you lose a lot of the particles when you have, in fact, strong observations that aren't noisy enough. So these are hard to implement. My own experience is that I like them because I like that people can fit the stochastic models, but they kind of either work or they don't. And when they're not working well for you, you can be stuck. So my talk today is to maybe revisit some classical Bayesian ideas and non-Bayesian ideas as well, but not in the focus of this talk, that complement this kind of methodology, that maybe let you do something like classical MCMC that's not simulation. Okay. And of course, these kinds of things are difficult. We have continuous time stochastic models, and a lot of the difficulty is coming from missing data. So this is the part that might be a little scary just because there's some math notation, but I want to at least fix ideas by giving a brief introduction to continuous time Markov chains, or maybe a brief review. So many people in statistics work with discrete time Markov chains all the time. So a Markov chain is, has a transition probability matrix of moving between states. In a continuous time Markov chain, the fundamental object, rather than this transition probability matrix, is an infinitesimal generator or transition sort of rate matrix. And so the entries of this matrix are the instantaneous jump rates between two states. So if I have states X and Y, maybe X is like 10 infected people and 70 susceptibles, and then Y is when you increase one infected in that population. So the probabilities are related to these instantaneous jump rates. And what that means is that that entry gives you the exponential rate before you would, the exponential waiting time before you would jump from state X to Y. Okay? So if you have all these candidate states Y you can move from a state X, then the total rate of leaving X is a sum of those exponentials. Right? And so in some sense, this just gives you a bunch of different competing rates for moving between states in your process. And if even if you haven't worked with these, the likelihood you would expect to be quite nice, because it's going to be a bunch of exponential events. And the first event to occur out of many exponentials is the exponential with the sum of the rates. There's a lot of very nice properties, and you end up having a pretty simple likelihood that's a product of exponentials. Right? So if I simplify this a little bit, if I were to do some math and collect like terms and take the log, you can write it in a way where all I really need is the total number of each type of transition, the jump between each type of state, as well as the dwell times that I spent in each of these states in my system. So basically what I'm saying is you can believe that the form of the likelihood is nice enough that I can collect it into simple sufficient statistics. I need the number of each type of transition and the total time spent. So equivalently, you can think about this as I need to know the exact time of events that occur in my continuous time process. And if I have this, then the likelihood is really, really nice to work with. It's an exponential family. I can derive, set the derivative equal to 0, derive this by hand. And if I want to be Bayesian, which I will in this talk, we can do nice conjugate relationships with pretty simple priors and just have very nice updates, deep sampling and stuff. So why am I saying that likelihood-based inference is going to be challenging, right? This is a really nice likelihood. And the key is, well, if I have access to these sufficient statistics, I can do everything really nice. But for instance, this one relies on the total number of events and exactly when they occur. And that's something we often don't have access to in epidemics from observational data, but also from many settings that I've worked on with continuous time processes. Like if you are studying the blood system that starts in the bone marrow and moves out into peripheral blood, and you have blood samples every week, you don't know all the continuous paths in between. So one example in the epidemic context, if I have incidence data, right, if I know that the total number of 4 infections occurred in a day or a week, then I don't know exactly, first of all, when these things occur, which contribute to the likelihood, nor do I even know the total number of infectious people at the beginning and end, because that also depends on the recoveries, right? So I might not observe the number of recoveries, and even if I did, I certainly don't know the times of events. So you can imagine that this is one continuous process over time that is explaining the data. Here's another, and there could be many such possible processes, right? They each have their own little likelihood. And as you know in statistics, when I want to incorporate sort of all of the possible likelihoods that I don't observe, and instead just want to describe the overall probability of getting from this state to this state, that is now like a transition probability in the usual sense, but it can be difficult to compute for many of these processes. So this is kind of the usual, like in a discrete time Markov chain, you have something like this, but the time increment is always 1 day. Now, I would like to work with the likelihood of my discretely observed data, right? Maybe it's every week. Sorry, I'm out of pointer. And I need to be able to relate those instantaneous rates and that nice likelihood to these marginal quantities, right? And I call them marginal quantities because they are marginalized or integrated over the set of all these possible step functions. So that marginalization is really hard. And I've worked a lot on that during my thesis for certain processes. And there's a lot of beautiful math behind that, right? It's like computing a hard integral and integrating over the missing data. And we use a lot of Fourier transform techniques, spectral techniques that I won't talk about today. I also want to mention, because especially if you've done continuous time Markov chains, you'll say, wait, Jason, if I want the probabilities, like the usual discrete time Markov chain, but for any time t, and I have the instantaneous rates defined, there is this relationship given by exponentiating that matrix. And the problem there is that this also becomes a computational bottleneck, right? Because this is going to be generally cubic in the size of the state space. You can do a little better with some sophisticated methods. But in our case, like if you have an epidemic of even, let's say, 100 individuals that are susceptible, the state space is not just size 100. It's the number of configurations of S, I, and R that sum to 100, which is huge. And for a real outbreak of thousands or millions, it's completely intractable to do this kind of thing. This works well for smaller state space models, even if they're complex, but you have a manageable number of states. Okay, does this make sense so far? Okay. So the strategy I want to focus on today to get around this missing data problem and sort of achieve this marginalization is via data augmentation. Right? So now, instead of what I didn't cover, the sort of Fourier techniques to compute that integral, we're going to try to get at the integral via latent variables and sampling. So just to kind of formalize the thing I just described, right? I'm observing data weekly, but what I don't observe are the continuous paths, which I denote Z, that run through my observed data that could give rise to it. And what I need to do is somehow integrate over a potentially very complex and high dimensional space of unobserved continuous time process paths. In fact, it's infinite dimension in this problem. So when I don't know how to compute this integral for like a nonlinear process, such as even the simplest SIR model, let alone when I extend the model, one we can get at this in a Bayesian perspective is to do something called data augmentation. And what that means is, well, the reason that this likelihood is difficult is because of this integral. But I'm integrating against Z in the complete data, where the complete likelihood would have been nice. So if you go all the way back here, this is the nice part that is appearing under the integral that I need to integrate part of it out. So instead, I could somehow just make use of that nice likelihood the whole time. Then maybe I could do inference on that object, which is maybe not surprising because it's kind of like saying if I observe the complete data, then I could do inference. So data augmentation seeks to complete your missing data by proposing possible values of the missing portions and fixing them one at a time. So if I propose, like, maybe I saw 5 new infections, but I'm going to propose one path for now, I can now look at the posterior distribution for the complete data, even though I originally was interested in theta given x. Okay? So if I'm able to expand my parameters, and now I'm targeting not just the parameters, theta maybe includes the infection and recovery rate, but also all the missing events. So now I have a much bigger posterior distribution. I'm trying to infer the missing events as well as the unknown parameters. Then I can make use of the nice likelihood in my computations, right? If I do something like Metropolis Hastings, the accept-reject ratio will be of a nice form instead of this difficult integral. Okay. And so I want to expand the parameters in like these latent variables and then draw from the joint posterior. So originally, like I said, this marginalization problem is hard. I couldn't do the integral here to do inference on theta given x. But if I have the posterior of z comma theta given x, and I want to get from that to theta given x, now it becomes trivial to marginalize. I would simply ignore all the latent variables, right? So if I have sort of like a table of z and theta, if I look at the sort of margins of the table, I simply just, count up all the thetas and ignore the z's and similar results. So this is something you convince yourself of, but basically shifting the marginalization to the posterior makes it trivial. Okay. And of course, the difficulty might still be to design a sampler that works well, that can actually propose and explore the unknown space of Z efficiently, right? That's kind of the difficulty with Bayesian inference. Like, it always will technically work, but we need to make sure it works well, and we don't we don't explore forever and run our chain forever. So what I'm hoping to make the case for today is that you can use classical MCMC rather than these simulation-based methods with designing carefully these proposals and using data augmentation like so. So this one wasn't really as mentioned in the abstract, but I think it's a nice motivation. So one example we'll talk about is not only will we be able to do exact likelihood-based inference for one of these models, but we'll also be able to incorporate more information by relaxing one of those fundamental assumptions, relaxing the well-mixing assumption when we have observed data on contact networks that are changing that contradict that assumption, but also tell us more about what's actually going on in the dynamics. So in this paper, which came out last year in JASA, even though it was finished a long time before that, we want to have a co-evolution of this SIR model with the contact network, right? So these people are changing compartments of their disease status, whether they're infectious or healthy, but also their disease status should affect how likely they are to start more interactions or stop interacting, and vice versa, right? If they're interacting a lot, you would think the probability of getting infected should be high. So there's a co-evolution there. And we're going to just use this to exemplify the data augmented strategy. Okay. So just what I mean by contact network data, we often have the case counts of who's infected and who's recovered every week, let's say. But we also, in this case, because it was an experimental study, have some mobile health data on the actual contact patterns in a high resolution manner. So 100 or so individuals on a college campus have this app on their phone that are basically continuously pinging. 5-minute intervals are more or less continuously monitored. So when they're close enough to each other, let's say within 6 feet of each other, their Bluetooth app will tell us that these two nodes are in contact. And then when they are further apart, they will not. And so we can observe just the networks empirically. And of course, they're not dense. So they're certainly not complete graphs like the well-mixing assumption would imply, but also changing over time. And so we observe this cohort for about 10 weeks with a fall break or something in the middle. And we see that they're pretty low network density, but certainly the contacts are changing. So we want to incorporate that into our model and move beyond that well-mixed assumption, right? So one might be interested in doing this when you observe the links that are present. And basically, there's a lot of interest in this because we have more and more high-resolution data that tell us this kind of thing, whether it's from Google or from these kinds of studies. And so the well-mixing assumption, if everyone is equally likely to come into contact with everyone, you can think of that as there's a complete graph, right? If you have 5 people in a population, they're all connected to one another in terms of potential infections. So of course, when we observe contact network, we're moving away from that. And so there's a very natural way to extend the SIR model that I presented. Right? If you're observing now a non-complete graph, we can encode that as an adjacency matrix, where the ones are there if there's an edge present at the time, and a 0 is otherwise, right? But we want to model this in a way that's evolving, so we actually took the simplest approach, which is just to say that there is a Markov process whose values switch between 1 and 0, and then those rates, there's a rate of switching from 0 to 1, and a rate of switching from 1 to 0, which means a rate of initiating and stopping contact. And so what we want to do is have those rates tied to the disease status of the nodes, right? That's kind of what we were saying, have this coevolution between the disease status and the network status. So basically with I and J, these two individuals are not linked right now. Then if one of them is infectious, one is susceptible, then we use those subscripts to denote the rate of them initiating connection or a contact. And simply, depending on their disease status, if they're already associating and one of them's like, hey, I'm sick, there's a rate of them breaking contact. So at the individual level, these are like rates of the ones going to 0 or the zeros going to ones in our network. And then, of course, you would like transmission to occur, and there's a natural way to generalize the SIR model, because if there's one edge present, then along that edge, there's a transmission rate beta. So there's sort of an exponential waiting time of beta that might occur as long as that edge is there. And similarly, if one of these people is infectious, there's a competing exponential waiting time of rate gamma of them recovering, right? So these are the kind of events that can occur in terms of the epidemic and the network. So basically in the simplest case, and I'm going to focus on Markovian things, but this actually extends beyond that surprisingly. So we have infections, recoveries, and link activations and terminations. And at the individual level, we've kind of already mapped them out. There's a rate beta per edge, a rate gamma that doesn't depend on the edges, depends on individuals independently, and then some kind of link rates that are occurring, these ones and zeros, adding and flipping. Now, if I want to aggregate this onto the population level, then this is kind of poor notation, but the infections will occur at a rate beta times, this is meant to be one quantity, SI. So SI is the number of links, the number of people in contact where one is infectious and one is susceptible. Right? You can imagine, first of all, if I have a complete graph, then the number of these links is exactly S times I, right? So in some sense, this is a strict generalization of the well-mixed case to count, to be more cognizant of the number of links that are currently present at a time. But that thing can change now. The recoveries are identical to the SR model because it doesn't depend on the network. And then these link activations depend on more careful bookkeeping on a number of different types of pairs of all statuses, which I'm just going to abbreviate with some notation. So the main thing here is to motivate the models and the likelihoods. I'm not going to go into detail on the network structures and bookkeeping quantities because the next slide does look scary. We have a likelihood that has all these, a lot more terms. But basically, I want to emphasize that it does take the same simple form as at the beginning of the talk, because it's just a special case of that general continuous time Markov chain likelihood. Which is to say, if I observe everything continuously, the complete data likelihood, now not only does it have the epidemic parameters, so the theta vector includes both beta and gamma like the SR model, as well as the network parameters. And what I want to mention is that it really is like before, you have basically the type of event for the rates, these are kind of the QXYs, exponentiated to the number of each type of event. And then you also have a term here that ends up being related to the dwell times in each state. And this integral, I'm writing it compactly as an integral, but this is something that's easy to compute. It's just summing up things based on what you observe. Like if you observe somebody's infected for this length of time, that person contributes a certain rectangle to this integral. So it looks scary, but as long as you have all the bookkeeping and the R code and you keep track of the notation, this is something that's extremely easy to compute. Right? You add and subtract a bunch of things to a log likelihood. If you work in this area, you might ask, well, why did you propose a new network model? There are some other network models out there with some very nice mathematical analysis by probabilists, such as Frank Ball and Tom Britton. And basically, it's a very similar model in terms of how they behave if you simulate data from them. But there's sort of different things you prioritize depending on what structure you care about. So in their approach, rather than appearing and deleting edges, they're more about rewiring. So the edges kind of switch places in the model. And for them, it's like important to retain vertex degrees to do some kind of mathematical analysis there in terms of asymptotics. For us, we want to be able to write down the likelihood. So we need something that resembles some kind of exchangeability so that we can write things down that don't get overly complex. Okay. Now, just like in the beginning of the talk, if I had the nice complete data likelihood, I kind of claimed that I can derive closed form expressions for MLEs and things like that. And that's the case here, right? I said there's more notation, but I could just differentiate the log likelihood, set equal to 0, get closed form expressions for all of the parameters. And also similarly, just as an example, set up with gamma priors in a Bayesian approach, that would just be pure Gibbs sampling, right? If I had the complete data. And so we just wanted to check all these derivations because they are indeed messy. And this is kind of a pain to code. But if you run a simulation study where you simulate from that model, and then you observe it for more and more events, so basically you're getting more and more data, we do see empirical consistency for these closed form estimators. So just to check that all the derivations are right, we see that, simulating like 4 different epidemics, we see that it seems to be consistent in terms of the estimation based on the ground truth, which is the black lines. Okay, so that's just kind of a sanity check for our math. But I want to focus on, right, the whole point of this talk is why is inference actually hard? So in the partially observed case, we'll need to combine that model with data augmentation so that we can actually do inference in a realistic setting, right? So realistically, we often have this kind of surveillance data in epidemic studies where we observe counts, maybe weekly or daily. They can also be irregular time intervals, right? So they don't have to be regular in this approach. And bringing back this picture to say that, we have a lot of unknown variables that prevent us from using these nice expressions here. So in our case study, we'll see that what we don't know at all is the recovery times. So certainly here we didn't know the recovery times. We also didn't know the infection times. For this data set, we'll assume we know the infection time in the contact network, but we don't know the recovery time. So there's still infinitely many such paths. So let's talk about the data. In this data set, we were revisiting sort of this causal study of influenza on a college campus by our collaborator, Alison Ayala. She was at UNC and has since moved to Columbia Biostats, or public health school, I should say. And so what they did is they have weekly intervals at which they collect health status reports, right? So this is the discrete part, the discretely observed part. Like every week, you kind of have a summary of who says they're feeling better. So they're kind of recovered by the end of the week, but you do not know when they recovered. We do more or less assume we continuously observe the network because we have this high resolution mobile health data. And so our latent variables is the set of recoveries times. We know how many recoveries there are, the new recoveries total, but we don't know the recovery times which play into the likelihood, right? So this is actually, there's not too much missing data, but the space of missing data is quite complex, right? Okay. And so in this approach, when I want to overview what data augmented MCMC looks like, in general, the sort of simplest manifestation of this is to sort of iterate between proposing the missing data, right? This is the data augmentation step. So given my observed data, I want to propose missing data that's consistent with it, right? I don't want to propose things that there's so many recoveries early on that I don't have any infectious people and it's not consistent with my observed data. So there's still a huge space of things that are consistent with our observed data, but it's also kind of constrained in a complex way, right? For instance, especially when you have this entangled with a network, you can't, like you usually have exponential recoveries, but then you need to deal with the constraint that you don't want somebody to recover if they're the only candidate that's connected to somebody that we know needs to be infected, right? Because then nobody could have infected them, et cetera. So there's sort of a lot of complex structure there in some problems such as this. but you want to be able to propose Z from a plausible distribution, or in the best case, to draw them directly from their conditional distribution of your data. And then given the data augmentation step, we now have made the complete data, right? Now we have X comma Z is like we have the complete data, at least one potential value of it. So then we can use the nice likelihood and use all of the stuff we like, use things like the Gibbs, things like Gibbs step here that are closed. So this is not the only way to do data augmentation, but it's kind of the primitive. And I just want to mention, right, if you're not Bayesian, this is maybe reminiscent of things like whether you want to think about EM from an optimization perspective or variational inference, which is kind of a mix of optimization and Bayesian stuff. There's often something that you might call a local update and a global update, or in case of EM, something that is sort of imputing or deriving a surrogate and then dealing with the parameters conditional on that. Right? So there's this alternating structure that comes up a lot when we're doing inference for missing data. Okay. So I'm not even going into the details of what this looks like for our method because it's a little bit messy, but I'll give you a flavor of it. Right, and also talk about why it's smart. So one, simulating from any kind of continuous time Markov chain when you need to condition on fixed endpoints tends to be a difficult problem. Right, so these simulation-based methods that I surveyed at the beginning of the talk, they're not fixed, they're sort of forward simulation. They're not fixing or conditioning on your observed data and drawing from their conditions. Right. And so, like I said, the constraints can be quite messy, especially when you have a contact network that's sort of very informative in what can and cannot happen. And of course, we're not the first people to do data augmented MCMC for epidemic models. There's a lot of very great literature coming out of groups like Warwick and other places in the UK specifically originally. So people like Gibson, Renshaw, a lot of these classic people in 2000 were doing metropolis-based things and a lot of reverse jump MCMC. But their method, even though they're following the same kind of structure here, basically how well it works depends on how well you're doing these steps. And their data augmentation or their proposal of the latent variables often were basically proposing sort of single site updates. So it's moving in a huge space very slowly and very incrementally, which causes your chain not to mix well. In our case, we're going to do something a little more sophisticated by leveraging the structure of the process. And another sort of subtle point is that even though the network here is making things much more complicated in terms of structure, in terms of how hard it is to code it, in terms of the math we have to do, it also constrains that latent space, right? So it's sort of reducing the size of where your Markov chain can explore or needs to explore. So there's advantages and disadvantages. That's kind of interesting. And then the surprising part, which I won't go into details about, is that network there, we can actually perform an exact Gibbs step. So that was derived by our brilliant grad student on this. There's a picture of this and there's more details in the paper. But like I said, it's not enough to just, or rather it would be already nice if you can just propose things that respect the network constraints in the sense that, you know, this is basically illustrating what I said. Somebody might want to, you might sample a recovery time for somebody, but then realize that that person cannot recover yet because they're the only candidate to infect their neighbor who we observe is infected in that week. So there's an algorithm that not only respects all those constraints, but is drawing the recovery times conditional on all this and conditional on the endpoints for the number of recoveries in a way that's from the exact conditional, right? So this is something our student Fanbu was able to derive exactly, which is very nice. So given step one, which I'm just going to draw a picture of, step two, conditional on the proposed latent data, I can update all the parameters in a super simple one-line way in R or something like that. And this strategy works really well in a lot of the things that we've done, including this. In the results of analysis, it's not too surprising. The main thing here was we wanted to demonstrate that the methodology can do joint inference on the network parameters and the epidemic parameters with exact uncertainty quantification, right? In the sense that we are targeting the exact model posterior, and sort of any error is Monte Carlo error, or of course they could be off because the model is wrong. But we're able to do sort of exact inference here, and it's more or less sensical with what the epidemiologists knew qualitative. So there's a big internal force of infection on campus. I didn't talk about it, but we actually relaxed the closed population assumption too, and there's an external force of infection. And the transmissions were quite slow, but the recoveries were quick, and overall the contacts were very slow. These numbers look kind of crazy because they're not normalized. So like this rate is a lot higher, but that's partly because there's so many more such links, potential links in the system, right? Okay, so this is actually mostly what I want to say about that case study, which it serves as a motivation for the sort of framework, the data augmented framework. But are there questions about that so far? Because I'm going to talk more about sort of how we're building upon this, but maybe at a higher level. So does that make more or less sense and as a use case of this Bayesian strategy? And so yeah, I think it's one of those things that you can probably believe if you've studied the basics of MCMC sampling, but it's kind of impressive that it can work well in these cases where you have a discrete state space and sort of a lot of missing data, right? Now, I want to talk about how the last application, we have a complex sort of network structure, but we also do have quite informative data. We're assuming we know the infection times, which are arguably the trickier part of the missing epidemic times, right? So what I mean by that is if you know when people are infected, the recovery dynamics are kind of independent, right? From your infection time, you have a recovery period, even though that might be constrained by the network. But because the infection dynamics are the part that's nonlinear, and like, for instance, identifying when an epidemic might really take off and ramp up could be the harder part of inference. And the more volatile part, we were interested in how we would extend this methodology where we don't see any of the latent space, right? So we have maybe total infections, which means we don't know the infection or recovery time, and they're correlated. So this becomes a really difficult problem. And so we were able to do this with a similar approach, right? Again, you want to construct the latent variables, which are both the infection and recovery time. So it's now super correlated and a lot more missing data. And we want to be able to do something like this, like I said, where you propose these and then propose the parameters. But as you might imagine, it's sort of difficult to propose the missing data in a way that's actually going to be efficient and to scale to large outbreaks, right? So I've kind of mentioned some previous results, but not only do they take small steps for the Z updates, but they rely on these things you never want to implement, like changing dimensions and things like that. So one of our more recent works, this is still a preprint, it was finished in 2022. And this is something that we don't really know how to motivate in general yet, but it is general. We've kind of used this strategy beyond this space. And it's that when you have a difficult likelihood because of things like nonlinear interactions or something like that, you can use surrogate processes. You can construct a simpler process that maybe decouples the complicated dynamics. But instead of doing inference under the approximate model, under an approximate likelihood, you can use that model as a proposal, but the whole stochastic process proposal. So you're proposing things jointly, and then you can correct for the discrepancy with a Metropolis Hastings step. So you're still doing exact inference under your complicated model, but now you have a very faithful proposal that's going to generate missing data trajectories that are actually close enough to your target model so that you can maintain a high acceptance rate and do inference tractable. So I don't want to go into too much detail on this, but the idea is, especially when you don't have infection times, the difficulty comes from the nonlinear infection rate, right? So in the simplest model, beta times I times S. Right, this is nonlinear, it depends on both of these interactions. So what if we could decouple this by saying, for instance, all we do is define a stochastic process on the exact same state space with the exact same parameters and things like that. But the interaction dynamic per week, let's say, is going to be S of t times a constant that's just one value of I, for instance, on the left endpoint, right? So in some sense, if I did this on the whole outbreak, and I also like didn't let I change as a population, this is very similar to like a branching and process approximation because I now have one population, which is S that I'm tracking. But this is more subtle. What we're doing is we're going to only decouple the rate. So S and I are both still stochastic processes that are going up and down, and they're still discrete state space. But not only that, this rate gets to reset every week. So based on the stochastic processes values, I on the left endpoint will be what it was under my surrogate model. But when I decouple these rates, inference becomes a lot easier because I have sort of a constant sort of homogeneous rate per individual each week, let's say. So you can now think of the components of your compartmental models as simpler, more tractable stochastic processes. And this is what I was going to focus the whole talk on, but it is more technical, and I wanted to give more of an overview and just give you the idea that we want to decouple difficult dynamics, use simpler surrogate processes that have nice properties to do that difficult conditional simulation step. So as an example, in this case, I claim that the first compartment is sort of now a linear process that's decaying. So it's called a linear death process. And one of the nice properties here that'll be important for sampling infection times is that we know the closed form distribution of the number of events in an interval given the number of total events. So that's a lot of words, but instead of looking at everything on the screen, what I want to remind people of is this nice, well-known property of Poisson processes, which are even simple, right? So if I say I have a Poisson process and over a week I observe 5 events, now I want to do conditional simulation, the hard thing. If I want to now say, what is the conditional distribution of when those events occurred, given that 5 occurred? Well, I can do it for the Poisson process. It turns out they're uniformly distributed, right? So that's really nice. I can just draw a uniform random variable between 0 and 1 week. And that is an exact draw from the conditional. So I can't do that for things like SIR process. That's the whole problem with conditional simulation of Markov chains in general. But for these block processes, this is basically analogous to that result for Poissons. It's kind of like a warped version of that, and you get truncated exponentials. So when I build up my stochastic processes with these building blocks, I will be able to propose things like, in the context of epidemics, the entire vector of missing infection times in a way that's really, really efficient and vectorized. But not only are they efficient and vectorized, if these decoupled dynamics are faithful, then these will very much resemble almost the conditional distribution of events under the SIR model, my original interested target of interest. Right? There's also a lot of nice properties now that we're back in MCMC land, right? Instead of dealing with very complicated plug and play particle filters, we can prove things. We can look at like classic techniques on showing that the parameter space is a small set and getting things like uniform ergodicity. So we have good guarantees on the mixing. And there's a lot of nice sort of algorithmic aspects that I've kind of talked about in words already. So I won't go into the details here. Just to kind of give you a sense of that construction I overviewed, why it's a good approximation to SIR. So here I'm plotting in color the sort of curves under the SIR model when I simulate from one seed under the stochastic model, the target the gray curves are from the true model. And then the colored curves are the same populations under my approximation model. So what I have is in the course of an entire outbreak, I've split the entire observation period into only 5 observations and then moving to, 10 and 15. So when I only have 5 observations, this is pretty crazy, right? If I saw the entire epidemic sort of ebb and flow, and I only observed the number of infected people 5 times, then certainly you can see differences in my approximation and the true dynamics. But even when I only have 10 observations, and certainly when I have 50 observations, you can barely tell the difference between the 2 processes. So, this is kind of showing that we would expect the proposals from the surrogate process to give us things like high acceptance rates. Of course, like just because the processes are pretty close, it doesn't mean that you can necessarily say the parameter inference will be close, which is why it's still desirable to use them as proposals within something targeting the exact posterior. And we're able to see that things work really well, right? So from the true model, you can simulate data and sample millions of iterations of the parameters in just a couple of minutes on a laptop. And not only that, when we start things far away from the truth, because we know the ground truth, we see that it's reaching sort of the right sort of modal area quickly, and it's performing well in terms of MCMD diagnostics. And it also works well in real data. So we have another slide comparing it to single-site updates, but unsurprisingly, it's mixing a lot better and is much faster in terms of expected sample size. But also on real data, so like this sort of a previous outbreak, which we focused on because, there's sort of a lot of, basically the COVID literature was sort of very, very crowded at the time. And there's sort of a lot of opinions on what things you should model. Whereas we're still building on the foundation, right? We're still looking at just count data here. We don't have vaccines. But this Ebola outbreak, which was a huge pandemic, this is something that has been mostly studied in ODE models. And we're able to, on this really large outbreak, we're able to also generate 1 million samples from our posterior in just one laptop in about an hour, right? So this scales really well. And we were able to get inference that sort of is consistent with the previous approaches, right? More or less, qualitatively, we see that the expected durations make sense. But again, this is for the first time giving us sort of draws from the exact posterior under the model in a joint way. Now, I mentioned that, some of you might think, well, the whole time you've talked about pretty simple models, everything's Markovian. But another nice thing about this Bayesian approach using data augmentation is that we can extend things much beyond the ways that I used to do it, much beyond the ways that we kind of do these integrals directly using transforms and things like that. So not only do we see that we relax the well-mixing assumption, but we can actually relax the Markov assumption. So things like the infectiousness period can be replaced by something non-Markovian and maybe more robust, such as the Weibull. And the likelihood still has a nice form. It's not going to be as easy, but in fact, the entire sampler still goes through in a way that doesn't require much additional computation at all. So we've done this on a lot of different data sets, in particular in oncology. A lot of times people believe like the phases, for instance, of cancer development, Markovian is not a good fit. And another way we're extending it and have extended it is to let that transmission rate not just be a constant modulated by the changing populations, but itself changing. And as you can see, there's going to be some trade-off here for overfitting, because if you let this beta be too flexible, then you don't even need the other parts of the model, right? I and S don't need to change if beta can change too much. But a lot of the previous work, which is very good work, uses sort of more Bayesian non-parametric flavor ideas, maybe Gaussian process stuff that can also be computationally intensive. And once we've laid down the sort of classical Bayesian machinery for R parameter inference, it's also not hard to put on things like priors enforcing sort of local constancy to get piecewise constant paths that provide a good data fit without overfitting, right? And it's very, very simple. So it doesn't add much to the computational overhead, which is important, right? Because my whole spiel here is that hopefully we can believe that we can do fully stochastic modeling and still do inference in a way that allows us to use familiar tools that we can extend and debug. And so it's continuous time Markov chain framework, and even with relaxing the Markov assumption, we get to use all this kind of familiar machinery that's well studied that we can prove things about, and we can apply to all sorts of related fields, right? So right now, field of epidemics, we're still incorporating things like when you have viral loads at a lower level from things like within host models, when you have multiple strains or compartments, other covariates. On the network side, right, we observed sort of a study that was contrived in the sense that it was an experiment. If you have observational data like general mobility trends from Google or something, you have missingness also in the network, and now you need actual good network models. You need random networks that are plausible for explaining that data, and you might want to do some similar imputation on the network. And of course, this kind of stochastic process model with nonlinear interactions or with a lot of heterogeneity across space or individual comes up all the time beyond epidemiology. And so systems biology, ecology, and all of these other studies. So we're exploring those things. And if you have those interests, I would love to chat more if you're convinced by anything I said today. So before I end, I want to thank sort of the people who did all the hard work. Fan was one of our PhD students and has since graduated and is now about to join Michigan Biostats. And she passed to UCLA, where I did a postdoc as well. Raphael is about to graduate this year. I am trying to sway him to do academic things, but he wants to work, because he's working on this epidemic stuff and he really does want to make real impact. He's quite interested in doing something like working at the NIH and really being hands-on with this kind of modeling on the data, which is lovely. And Jenny actually did a lot of the time-varying beta stuff. She was an undergraduate in my group, which was super impressive. She wrote a first author paper there, as well as helping with a lot of other things. But she's already committed to MIT. She's working with camera, but hopefully you'll all have a lot of encounters with these people in the field later on. They're really wonderful to work with. So just a limited set of references, some of the papers that I talked about that are related to this talk today. So thank you for your time. Question. There's sort of different perspectives. So if the discrete state space can sometimes be harder, right? I mean, you certainly can't apply some of the general methodologies that work well for continuous stuff, like HMC understand and things like that. So the methodology becomes different. And sometimes things like slice samplers can play really well with the continuous case. But so things are different. I wouldn't use this strategy, but partly this strategy is difficult. This strategy is nice because of the difficulties in the discrete case, right? In the continuous case, there are very similar data augmentation strategies too that are well developed. So you can still do things that propose latent paths one way or another, and they're very related to. In fact, like a lot of these discrete strategies are kind of motivated by the existing stuff there. So a person who's done a lot of work there on continuous time Markov chains and data augmentation is Vinayak Rao. So and he worked with Iwete on that stuff. So a lot of it comes out of Gersonov's theorem if you work on those continuous processes. This is very nice. Good question. Mm-hmm. Sorry, is it what? Giving better prediction. So certainly, we haven't focused on prediction too much, but it certainly does a lot better prediction than the deterministic counterparts. The thing is, like, there's a lot of sort of papers where there's a lot of aspects of the model, and they seem to do well in prediction. But what I'm saying is, like, I don't really trust the inference under those models because they're kind of engineered to do good prediction on the particular use case you have, but they might not generalize to other places. And I don't know what I believe about the parameters, right? But this does better prediction than the deterministic models. And one we did, which I didn't talk about today, was more focused on forecasting, and it was on ICU bed occupancy. So that one we have a sort of immigration, birth, death process, and the prediction on that was actually really good. It kind of surprised us. It's a simpler model though than the nonlinear ones, with similar ideas. Thanks. Thank you.